Chapter 1. Chemical Reactions and Equations, up to 1.2.2. Decomposition Reaction. Q. What is a chemical reaction? Give examples. A chemical reaction is a process that involves the rearrangement of the molecular or ionic structure of a substance, as opposed to a change in physical form or a nuclear reaction. In a chemical reaction, reactants are transformed into products. Examples. Burning of magnesium ribbon in air, 2 mg of S plus O underscore 2 grams, right arrow 2 mg O of S. Formation of water, 2H underscore 2 grams plus O underscore 2 grams, right arrow 2H underscore 2 OL. Q. State the law of conservation of mass. How is it related to balancing chemical equations? A. The law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. This means that the total mass of the reactants must be equal to the total mass of the products. Balancing chemical equations is directly related to this law because it ensures that the number of atoms of each element on the reactant side is equal to the number of atoms of the same element on the product side. This makes sure that mass is conserved. Q. What is a decomposition reaction? Explain with examples including thermal, electrolytic, and photolytic decomposition. A decomposition reaction is a type of chemical reaction where a single compound breaks down into two or more simpler substances. It is generally an endothermic reaction, requiring energy in the form of heat, light, or electricity to break the bonds. Examples: thermal decomposition using heat. Heating of calcium carbonate, CaCO underscore 3s, x right arrow text heat. CaOS plus CO underscore 2 grams. Heating of ferrous sulfate, 2FeSO underscore 4, x right arrow text heat. Fe underscore 2O underscore 3s plus SO underscore 2 grams plus SO underscore 3 grams. Electrolytic decomposition using electricity, electrolysis. Electrolysis of water, 2H underscore 2O, x right arrow text electricity 2H underscore 2 grams plus O underscore 2 grams. Photolytic decomposition using light. Decomposition of silver chloride, 2 silver 1 chloride, x right arrow text sunlight, 2AgS plus Cl underscore 2 grams. Decomposition of silver bromide, 2 silver 1 bromide, x right arrow text sunlight 2AgS plus Br underscore 2 grams. Used in black and white photography. Chapter 5. Life Processes, Nutrition and Respiration. Q. Differentiate between autotrophic and heterotrophic nutrition. Give examples for each. A. Autotrophic nutrition. In this mode of nutrition, organisms synthesize their own food from simple inorganic substances like carbon dioxide and water, using energy from sunlight, photosynthesis, or chemical reactions, chemosynthesis. Examples: all green plants, cyanobacteria. Heterotrophic nutrition. In this mode of nutrition, organisms obtain their food by consuming other organisms or organic matter produced by other organisms, as they cannot synthesize their own food. Examples: animals, humans, cow, dog, fungi. Q. Describe the process of photosynthesis. What are the raw materials required and what are its products? A. Photosynthesis is the process by which green plants and some other organisms use sunlight to synthesize foods with the help of chlorophyll, carbon dioxide, and water. It occurs primarily in the chloroplasts of plant cells. Process. Light energy is absorbed by chlorophyll. This energy is used to convert carbon dioxide and water into glucose, a sugar, and oxygen. Word equation. Carbon dioxide plus water x right arrow, text sunlight, chlorophyll. Glucose plus oxygen. Chemical equation. 6CO underscore 2 grams plus 6H underscore 2 OL, x right arrow text sunlight, chlorophyll. C underscore 6, H underscore 12O underscore 6AQ plus 6O underscore 2 grams. Raw materials required. Carbon dioxide, CO underscore 2. Water, H underscore 2O. Sunlight, chlorophyll. Products. Glucose, C underscore 6, H underscore 12, O underscore 6. Oxygen, O underscore 2. Q. Differentiate between aerobic and anaerobic respiration. Give examples. A. Aerobic respiration. This type of respiration occurs in the presence of oxygen. It involves the complete oxidation of glucose into carbon dioxide and water, releasing a large amount of energy. It primarily occurs in the mitochondria. Equation. Glucose plus oxygen right arrow, carbon dioxide plus water plus energy. C underscore 6H underscore 12, O underscore 6 plus 6O underscore 2 right arrow 6C, O underscore 2 plus 6, H underscore 2O plus text energy. Examples. Most animals and plants. Anaerobic respiration. This type of respiration occurs in the absence of oxygen. It involves the incomplete oxidation of glucose, producing less energy compared to aerobic respiration. The end products vary depending on the organism. In yeast, alcoholic fermentation, glucose right arrow, ethanol plus carbon dioxide plus energy, C_6, H_12, O_6 right arrow 2 C_2 H_5 OH plus 2C, O_2 plus text energy. In muscle cells, lactic acid fermentation, glucose right arrow, lactic acid plus energy, C_6 H_12 O_6 right arrow 2 C_3 H_6 O_3 plus text energy. Examples: yeast, some bacteria, human muscle cells during strenuous exercise. Chapter 9, Light Reflection and Refraction till 9.3.2, Refractive Index included. Q. State the laws of reflection. A. The laws of reflection are: 1. The incident ray, the reflected ray, and the normal to the surface at the point of incidence all lie in the same plane. 2. The angle of incidence, the angle between the incident ray and the normal, is equal to the angle of reflection, the angle between the reflected ray and the normal. Mathematically, angle I equals angle R. Q. Define refractive index. What is its significance? A. The refractive index n of a medium is a dimensionless quantity that describes how fast light travels through the medium. It is defined as the ratio of the speed of light in vacuum C to the speed of light in that medium V. Formula: n equals frac text. Speed of light in vacuum text. Speed of light in medium equals frac circa versus. Significance: optical density. A higher refractive index indicates a greater optical density of the medium, meaning light travels slower through it and bends more significantly when entering it from a less dense medium. Extent of bending. It quantifies the extent to which a ray of light changes direction when passing from one medium to another. Material identification. It is a characteristic property of a material and can be used to identify substances. Q. Explain Snell's law. A. Snell's law, also known as the law of refraction, describes the relationship between the angles of incidence and refraction and the refractive indices of two different media. Statement. For a given pair of media and for a given color of light, the ratio of the sine of the angle of incidence sin I to the sine of the angle of refraction sin R is constant. This constant is equal to the ratio of the refractive indices of the two media. Formula: frac sin I sin R equals frac n_2, n_1 equals n_21, where n_21 is the refractive index of medium 2 with respect to medium 1. Alternatively, it can be written as _1 sin I equals n_2 sin R, where n_1 equals refractive index of the first medium, where the incident ray travels, and n_2 equals refractive index of the second medium, where the refracted ray travels. I equals angle of incidence R equals angle of refraction